All right. Welcome, everybody, to science time. Let's get science every time. All right. Now, if you don't already know, my name is CJ, and I am your host. We have a fantastic talk for you next month, February the 17th. We've got problems with the door, but we got Tom Hisson on birding the world. The world. He studied natural resources and environmental education at OSU. He's been a naturalist and education manager and a curator of education. So he's going to come and talk to us about birds. Cool. Tonight, however, we have the wonderful, fantastic, and fabulous Cisco Sugui. Now, he's going to be talking to us about satellites and other things that we put into orbit. Cisco has a mechanical engineering degree from Cal Poly. He's a former spacecraft engineer, and he has the patent for non-uniform spacecraft body design. Super cool. All right, take it away, Cisco.
Yep. Hey, CJ, any chance you could point the laptop camera over to the audience so I can see you good folks?
You mean you don't want to look at the ceiling?
Yeah.
Sorry, I did not think about that. There you go. Is that better?
Yeah. Okay, folks. Good. Yeah, good talk to you folks. So yeah, again, so this is very, very informal. So feel free to shout out any questions. I don't know what you guys don't know or what you guys are interested in. So I'll try to present some stuff, and you guys shout out if there's anything you guys want me to do a deeper dive into or explain a little bit more. All right. With that out of the way, let me see if I could share my presentation. Oops. Let's see. Okay. Let me get this thing in presentation mode. Oops. All right, satellites. And this isn't one of the ones I built, but it's representative of what we put up there. So just as a basic definition, a satellite is an object that moves around another object. And of course, the man-made ones are the machines that we launch out there, and they'll either orbit Earth or other celestial bodies. What do we use them for? The highest use or the largest use that we do with them is communications, followed by navigation, and then content broadcasting. We do a bunch of weather and surveillance. Obviously, the military uses them a lot to keep an eye on everybody else. And unfortunately, the last thing or the least usage that we do with them are scientific studies. Of course, there's some other oddball ones here and there. And I'll try to dive into some of the more interesting scientific studies in a little bit because it's really fascinating what they can actually do, with something that's about 200 miles up in the air. Okay, so just before I start, so just a little bit about me. Right out of school, this is how I started my career building these spaceships. That's me on the lower right. The one on the upper left is a typical commercial satellite that we build. It's about the size of a semi. It's about 2,500 or so odd pounds. If we build them for the military, the paperwork that goes with it is about the same weight. But about a ton of documents or so. So the outfit I work with is Space Systems Loral. I spent 10 years there. Designed and built roughly about 10 of these things. Takes normally about a year and a half to design and build one of these things. Back in the day, it was around 250 million bucks for each one of these. That's not counting the cost to stick them on a rocket and put them in orbit. The rocket itself is anywhere from $80 million if we use the cheap ones from the Russians to 120 million if we use the expensive French one. American rockets are somewhere in between, but they don't quite have as much payload capacity. I mean, I hate to say it, but the Russians had the strongest launch vehicles on the planet until we can get the next generation out. Okay, and again, if you guys have any questions, feel free to ask. The satellite that's kind of shown here doesn't have the solar panels yet, so this is just the main body itself before we start attaching stuff to it. Okay, so just quick question out there. Anybody know how many artificial satellites we've got around in orbit right now?
10,000?
Oh, well, that's actually not a bad guess. Let me share something with you folks. Let's see if this will actually do it. Uh, can you guys see this?
Yeah.
So this is a web link to, I think, University of Austin. Anyway, they're tracking all of the man-made items that we have on there. The golden dots are, the satellites that are actually still active. The amount of stuff we have out there is actually uncountable. It's probably greater than 10,000. But just the living satellites are all in gold, and then everything else are just floating space junk. So that's either the rocket bodies, spacecraft debris, or pretty much anything larger than a softball. That's how much we've got floating out there. This golden ring that you see around the planet, this is the geosynchronous satellites, and I'll get to some of the definitions in a little bit. This is pretty much the only place in orbit where we can park a spacecraft and have it kind of sit still in the sky. Everywhere else, the satellites are kind of moving in an intricate orbital pattern. Okay. So let me just get back to the presentation. And just as a brief trivia thing, so the very first thing we ever sent out there, and fortunately the Russians beat us, is Sputnik, or was Sputnik, launched in January 4, 1958. And the Sputnik is actually Russian for companion, which is what they called satellites back in the day. Okay, so some quick classification of the satellites we put up there. It's broken down by function and also where in the sky we put them. So the lowest orbital pattern or orbital altitude is what we call LEO, or low Earth orbit. It's anywhere from 100 to 1240 miles. So this is good for Earth observations and some communications. The bad thing about this orbit is that's where a lot of, or most of the space junk are, because usually this is where the second stage kind of separates on a multi-stage rocket. Some of the famous things that are in low Earth orbit includes, the Hubble telescope, Starlink, that space-based communications network by Elon Musk, and the International Space Station. When you're in this kind of orbit, you kind of tend to go pretty fast across the sky. And I'll actually get into just a touch of orbital mechanics after this one. Well, essentially, basically, the lower in orbit you are, the faster you need to go in order to keep from falling down the gravity well. Above that is the medium Earth orbit. That's from 1240 to 22,000 miles. So these are more for multi-purpose spacecrafts. When you're in low Earth orbit, you see more. You zoom past Earth a lot more, but you only see a little bit of it. So the higher up you go, you can see a lot more, or you can cover a lot more of the planet. So that's why that's where they put the GPS satellite. So they can cover more ground with less orbiting bodies. And then the last bit of orbits that we use is called the geostationary orbit, which is 22,236 miles above the ground. So this is good for communication and weather observations. The bad of it is it's pretty far away, so it takes a lot of fuel to get up there, and it's pretty far from Earth. So some of the things, or one of the more famous satellites that are up there is things like DirecTV, things that broadcast back down to Earth. Now, you'll notice that for LEO and MEO, it's actually a range of miles. For low Earth orbit, it's from 100 to 1,200 miles, and then MEO is 1,200 to 2236. But geostationary orbit is an exact number. It's 22,236, and there's a reason for that. The reason for that is the way things stay in orbit is it's always a balancing act between the forward velocity of that object and the gravitational force being exerted on that object by the planet. So the further away you are, the less the gravitational pull, the slower you have to go, the slower you have to be in order to not break orbit. Now, if we want something to orbit the Earth at exactly 24 hours, so we can kind of keep it in the same spot, relatively in the sky, it has to be this exact distance. Any lower, it'll have to go faster, and then it'll start to drift. And any further away, and it'll orbit. Its orbital period is longer than 24 hours. So that's why a geostationary orbit is exactly this high. And not only that, the only place where we can actually park a satellite in the sky is in the equator. That's why you'll notice for people with satellite TV, the dishes are always pointed south because all of the satellites are over the equator. And every country on the planet are allocated a certain amount of parking spots for their satellites. So the U.S. has a certain amount, and that's where we put all our geostationary spacecrafts. Okay, any questions on that?
A lot of good information.
Okay.
Do we know how much Sputnik cost?
I'm sorry?
Do we know how much Sputnik cost?
Oh God, it's well, I don't know in terms of the actual money, but back then it was a space race. So pretty much the U.S. and the Soviet Union, they were working on, whatever the hell it costs, we got to be first. We got to have bragging rights. So they just threw bodies and money at it. So even though Sputnik itself, I mean, by today's standard, it's not very technologically advanced. It's only 22 kilos. It's in the trillions of dollars in today's money in terms of the effort that the Soviets took to put it up there. Okay. All right. So just a quick primer on the basic parts of a spacecraft. So most spacecraft will follow this configuration, but there are some notable exceptions. I'll kind of get to. So first on the upper section, there's a transmit and receive antenna. Obviously, we need to have a way of communicating with it, and a lot of the commercial satellites will beam back something. For example, Sirius radio will beam down digital radio. Satellite TV stations will beam down digital streaming signals. So that's why we have those there. Then we have the two thin rectangles on the side is where we have the payload. Essentially, that's the paying portion of the satellite, or that's what earns most of their money. We have solar panels on either sides. Almost all satellites will have this thing, with the exception of we do have some SpySats and other satellites that people, or rather governments, don't want us to spot. So they would normally not put big solar panels on them because they're like just big giant giveaway that something's up there. But generally, solar panels needs to power the spacecraft for at least not just power the spacecraft during the daylight hours, but also generate enough power so it could store it during the time when it's in the planet's shadow. So usually, well, on a geosynchronous spacecraft, that's 12 hours of sun and 12 hours of darkness. So the solar panels need to be able to supply enough power to accommodate both. Then we have the transponder and guidance and controlling command and data processing units. So here's a fun fact. The processing power of a normal spacecraft is probably 1/100th or 1/1000th of the processing power that you have in your cell phones right now. The computing technology that we put up there, or at least back when I was building them, we used 1970s technology, and that's because up in the region where they need to work, there's a lot of solar radiation, and there's a lot of electromagnetic effects from the sun. So complicated processors like the one you'd have in your phone, they would be susceptible to errors. So that's why we tried to put the simplest, most robust calculating devices that we could put up there. So they're essentially dumb terminals. So spaceships really aren't as advanced as most people think, mainly because we need to make them as dumb, simple, and robust as we can. Because once we put these things up there, their service life is around 10 to 15 years. So imagine not being able to service anything for that long, and it needs to work during that whole time. So a lot of the things that we do, one of the ways we account for that is by building in a lot of redundancies, so that on any given spacecraft, 1/3 of the systems could fail, but it could still keep on working. Okay, the big circular thing in the middle is the fuel tank, but I've really oversimplified it. The propulsion system of a spacecraft, the fuel that it has is normally comprised of like 3 elements: the fuel itself, and then what we would call the oxidizer, because there's no air up there, there's no oxygen, so it needs to have an oxidizer. And then lastly is a pressurant, because there's no gravity out in space. We need for a way to get all of the fuel onto the thrusters. And if we just simply pressurize the fuel at the end of the spacecraft's life, there will still be some fuel left in the tanks that we can't use because it's too weak to get to the thrusters. So that's why we have a pressurant system to essentially squeeze the tank, sort of like a tube of toothpaste, to get every drop of fuel out of there. And and then the batteries. These are normally these are actually pretty hefty batteries. The commercial satellites, at least back when I was building them, they operated at 3 kilowatts. So imagine having to draw 3 kilowatts of power for about half the day. So that's how big the batteries needed to be. Thrusters. Even though there's no air out in outer space, or at least not in the higher orbits, there are some disturbances that these spacecraft need to account for. Every time the moon passes by, it'll kind of disturb the spacecraft a little bit. So we need to expend some fuel, kind of getting them back into position. And then there's always solar wind as the spacecraft comes around the shadow of the Earth, and sunlight hits it for the first time that day. It'll get disturbed. So this disturbance are kind of minor, but it doesn't really take much to throw off the alignment of spacecraft. And for a lot of things that we send up there, the pointing direction is super critical. Okay, any questions on this one?
Yeah, I do. You have the dishes for the transmitter and receiver as being
Yeah.
2 different sizes. Is that on purpose? And I would have thought it would have been reversed. I would have thought that the receiver would have been bigger.
Oh, okay. So my background is actually working on commercial satellites, things like DirecTV. So the big moneymaker for that spacecraft is the signal that they send back to the planet. So that's why they have such a big. Normally, the transmit antenna is pretty big, and most of the payload is devoted to sending these signals back down to Earth. But you're absolutely right. If you look at, say, the space probes that we sent out of the solar system, like God, I'm sorry, I'm drawing a blank, but like the Galileo spacecraft, the receive antennas are huge, just because they're meant to go really further out, and at those distances, the signal from Earth is really weak. So yeah, depending on the use. Commercial spacecrafts, normally the transmit is the moneymaker, so it'll be bigger. But for a lot of the scientific based spacecrafts, it's the receive will actually be big, because they're not broadcasting it to general users. But yes, it could be any size depending on the use.
That makes sense. Thank you.
No problem.
Go ahead.
Oh, okay, so my question is about the interruption of communication by solar activity.
Mhm.
How bad is that? How frequently is the satellite's communication completely disrupted by solar activity?
It doesn't happen very often, because the big danger of solar, well, it happens during what they call a coronal ejection activity, or where the sun will suddenly burp out a large mass of charged particles. Thankfully that doesn't happen frequently, and thankfully the times where it would discharge so many particles that electronics are at risk is not that often. So we would have like that kind of event, like maybe once every couple of years. So a lot of times you don't even see these interruptions. And usually we operate at a frequency band that's not really susceptible to the radio waves from the sun. So hopefully I'm answering your question, but it's not very often that it happens. And we do have some contingencies for when we see like a big coronal ejection that's about to happen. We would sometimes turn off the satellites until the danger passes. But as far back as I can remember, this only happened once in the past 6 years or so.
Thank you.
Okay, somebody else had a question?
Yeah, what type of fuel do you use, and what type of battery rechargeable battery technology?
So God, I wish I had the exact chemical composition of fuel, but it's called MMH. It's a monomethyl something hydride. Okay, well, I guess let me back up. Uh, for spacefaring technology, there's a lot of actually different propellants and different oxidizers that are used. The space launches that you see when they're like the space shuttle and those big rockets that carry satellites up to space, they normally use liquid oxygen and liquid hydrogen because that's how much you could pack a lot of energy in the same in the least amount of mass. Because when they combine, they will explosively just turn into water and vapor. The Russians they use kerosene and oxygen, just because they're kind of pretty old school. There's an outfit down in Southern California. His name is Burt Rutan. He's one of the first civilian people that sent a spaceship out into to outer space. He used vulcanized rubber and nitrous oxide. So there's just yeah. So I'm sorry.
Oh, we're just laughing.
Yeah.
So,
Yeah, but there's been a lot of different fuels that's used. The ones we use for spacecrafts, it's chosen because it leaves the least amount of deposits. Obviously, we can't use oxygen and hydrogen because it'll turn to ice as soon as it leaves the thrusters and it'll start forming around the spaceship. So we kind of use things that will leave the least amount of residue because there's a lot of sensitive surfaces on the spacecraft itself. Okay, and your question about the battery. Back in the day, we used nickel. It's not lithium. It's a highly compressed nickel-based batteries.
Nickel
I
metal
mean,
hydride?
yes, thank you. It's nickel metal hydride pressurized. So I think 600 psi. Um, just full banks of these guys. They're the ones that can actually take the abuse of being up there for about 10 years, and it could take the temperature swings too.
Oh, okay, yeah, because lithium hates the cold.
Yes, it does. It loses like 20% of its capacity in the cold, and it gets, and the temperature swings in these things it's phenomenal. It could swing from by 120 degrees either way on the course of a day. In fact, one side of the spacecraft could be boiling, that is 100 degrees C, and then the other side could be below freezing. That's how extreme it is. Okay. Any other questions? Okay. Good questions, by the way. All right, so just getting on to like interesting payloads that we've sent up there. So one of the interesting things, or one category of interesting things, are animals. So the very first terrestrial being to go up there is Laika, sent up by the Soviets in 1957. And that's one of the other things that we need to give thanks to our dogs about. They actually pioneered the space exploration, followed by Belka and Strelka in 1960. And those were the first Earth-born animals that actually went up and successfully came down. On the U.S. side, we got Ham, a chimpanzee that predated our astronauts. Of course, we sent up a bunch of insects, arachnids, and bacteria. So I'm just listing the animals that did not go into the International Space Station. In the International Space Station, they've conducted over 2,000 or so odd experiments. So I'm almost not counting them because if I were to go into the stuff that they're doing on there, it'll take hours and hours and hours. But just in general, the stuff that we've sent up there on a regular rocket and spacecraft is kind of amazing. Questions on this one?
do you have any information on I think they had like rats that gave birth in space, just to see how that would work with animals giving birth in space?
I don't have any information on that. One thing I do know, actually giving birth in space is actually pretty dangerous. One of the things that they've discovered is that I'm sorry.
On the ISS?
I think so. Yeah, they had like some of the rat mothers were just apparently weren't very good and let their babies float off, and others wrapped their babies and held them to them to keep their babies alive. Like, it was crazy. some of them knew what to do and took care of their babies while others just let them float away and die, so. It was fascinating, but anyway.
Well, yeah, well, it's kind of dangerous to give birth up there for one of the experiments that they ran up there is what would happen to bacteria in microgravity, and one of the things they found out is they grew faster and they're stronger. So any kind of infection is bad, but for higher level life forms like multicellular creatures, our immune systems actually go down. So it's a kind of a bad combination. So anyway, don't get sick in space. And then the other thing is in free fall or in microgravity, you feel like you're constantly falling. So it doesn't surprise me that some rat mothers would kind of like just like not know what to do in that kind of environment.
Right.
Yeah. Okay. So other interesting payloads that we've sent up there. So we've got telescopes. So the famous ones is Hubble, James Webb, Chandra. We send things up there because at least it gets the observatories out of the outside of the Earth's atmosphere, so we can see further. Satellite gravimetry, so Grace 1 and 2. So the funny story about this one. So Grace 1 and 2, these are two satellites that we sent out there to measure the fluctuations or differences in the Earth's gravitational field. I mean, we all think that gravity is pretty constant, but it really isn't, because at the crust of the Earth, there's some differences in terms of like land mass and things that are on there. So the way they measured gravity was that they had these pair of satellites, and they had them in a parallel, not parallel, but they had them on the same orbit, essentially tracking the same path. So when one of them reaches a region of slightly higher gravity, it would get there would be a slight tug on it, and those two would measure their distances relative to each other. So the satellites knew, okay, there's a slight pull on one of them, so we must be entering a region of higher gravity. Now, the precision of the measurement is these two satellites were about 220 miles apart, and they're able to measure a difference of distance about 1/10 the width of a human hair, which is about 10 microns. From a 220-mile distance. That's how they're able to like map the Earth's gravitational field. So that's one of the things. And forgive me, I'm like a geek out over these kind of things. The big challenges with conducting experiments in space is that a lot of times we can't do direct measurements of things that we're interested in. So we sometimes have to measure something that's a stand-in for something that's a stand-in for something else that we're really interested in. In this case, the two satellites are measuring the frequency shift of something they're beaming to each other to measure their respective distance, to measure the gravity gradients as they sweep across the planet. And from those measurements, they can figure out things like how thick is a glacier, how deep is the ocean, what are the where are the water currents going, because water currents will change the density of seawater, so they can actually measure ocean currents from outer space. So which I thought was kind of cool.
Very cool.
Okay.
When you said you were measuring up to 10 microns, what was between two what?
Between two satellites that were 220 miles apart. So they're constantly measuring how far apart they are.
So when
and
they
if one of them,
go ahead.
Sorry, what was the question?
So when they're measuring that, is it like line of sight, like in a straight line, or is it the distance in the orbit, like in an arc?
Line of sight, because again, these two are moving as a pair, and when one of them hits a patch of higher gravity, it'll get pulled or pushed. I mean, it'll get pulled, for a little bit until the other one catches up. So that time when it's slightly further away, the two are constantly measuring that, and they're also tracking the other the GPS satellites, so they know when it happened and how much stronger that localized area of gravity is.
Do they use like a laser, or would it be more of like a radar?
More like a radar, but not like how you think about it. So what they're actually doing is they're sending out a signal in the K-band frequency. So they're actually measuring the slight shift as they're slightly further. So anyway, just I mean, it's really, really super precise measurements. I mean, it's unbelievable. Okay. Any more questions on Tom and Jerry?
No.
Yeah, I mean, it's mind-boggling. I mean, to me, it's because they actually figured out, okay, we can kind of do this to measure this, that measure something else. But yeah, I mean, we're the things that we can actually measure are kind of limited. The atomic clocks we sent up there, they're doing that to actually prove or disprove parts of Einstein's theories because relativity. There's really very little ways we could measure it other than okay, if one atomic clock is moving faster than the other one, what is the change in time? Um, the other one are another interesting thing that we sent up there are space internet routers. So my company is kind of involved in this one. We're actually laying down the foundation for, one of these days, we might have a base on the moon, we might have a colony out in Mars, but so we're going to need to extend the internet out that far. So the way we've been communicating before is, we just send line of sight radio signals. But in the future, as demand for bandwidth grows, that's not going to be enough. So we're going to need to be a little bit more thoughtful about how we send information traffic back and forth. So, but we're planning ahead for a space-based civilization. Another one are crystalline-based electronics. So there's a Parker solar probe that we sent out to the sun. It actually got to touch the sun's corona. So that's about 2,000 degrees on the outside. So normal electronics would have melted long before reaching that temperature. So they actually grew some of the insulation out of sapphires and the conductors out of molybdenum. I thought it was kind of interesting. Alternative-based circuitry. Another one is Starman, which was sent out by Elon Musk when he was testing out his heavy lift rockets. Now, a lot of people, was thinking, okay, this is a stunt, but they can't really appreciate the effort it takes to put a Tesla up there. They actually have to prepare the vehicle quite a bit because Teslas are not meant to go into outer space. So things like you have to let the air out of the tires because at zero air pressure, tires are gonna explode, and it's gonna be like a little miniature thruster that's gonna toss the rocket out of out of its own core. So things like that, and there's a lot of the plastics with we call this phenomenon outgassing. And that's why we build satellites in clean rooms because any kind of dirt or grease that you put on a satellite, it'll tend to vaporize in the vacuum of space, and that acts like a little miniature thruster, which would kind of push on a spacecraft. So all the plastics have to be specially coated or made inert or replaced outright because, again, a lot of the stuff in a Tesla were never space qualified. But at any rate, so from the time they launched it, I think it was I want to say 2015 or 2019. It's already made about 6 or 7 orbits. The orbital path of this Tesla is between Earth and Mars, and they're saying that it has about a 22% chance of hitting Mars or the Sun, and hitting Earth is somewhere in the teens in the next couple of million years. But thanks to Tesla, thanks to Elon Musk, the chances of getting into a car accident in outer space is no longer 0.
Right.
Yeah. Which actually takes me on a different tangent. So all these commercial satellites, so I just want to toss this out there. All these commercial satellites, at the end of their life, I guess what we do with them? Nope, because it takes a lot. Well, it takes a lot of fuel to get them up there, and to bring them back down also takes quite a bit of fuel. And fuel is like gold. It takes about 100 pounds of fuel to bring 100 pounds of anything out there. And also, you also run the risk of like hitting somebody, which is like a big liability. So what we do with our commercial satellites is, and actually a lot of the satellites, at the end of their life, we actually send them to what we call a graveyard orbit, which is far beyond a geosynchronous orbit. So they'll orbit the planet for about 5,000 or 6,000 years before coming back down. Well, we're kind of thinking, 5 or 6 thousand years from now, it's somebody else's problem. But it's a lot safer than having them come down in reentry. A lot of the stuff that we put on these things are stainless steel, titanium, aluminum, very, very strong stuff, and a lot of them will most likely survive Earth reentry. Okay, some more stuff that we sent out there. So we have the COBE, the Cosmic Background Explorer, the Cosmic Radiation Background Explorer, rather. We sent a couple of gravity wave detectors on there. So these are laser-based. I think they're laser-based gyroscopes, so that we can actually measure any kind of small disturbances by gravity waves. And the advantages of that is gravity waves are not blocked by dust and gases in outer space, so we can actually see through nebulous. Anyway, we can see through the other side of things where visible light are stopped. Another critter that we sent out there are tardigrades. So this is a UK spaceship that was sent out there, but the UK scientists decided, okay, they'll put some living tardigrades on there, and the satellites spent 10 days in space before coming back down, and at the end of 10 days, in the hard vacuum of space, unprotected to the radiation, they saw that 6 to 8% of the tardigrades survived. I mean, 6 to 8% with no air and no protection from solar radiation. So that's just that's just phenomenal. And then the last interesting things that are out there is the ISS Presso. So this is a space-based espresso machine on the International Space Station. I mean, they spent quite a bit of money on this one. So any kind of R&D it's like millions, for NASA, just to make sure it'll actually brew an espresso in 0G. Okay, moving on. So what does the future have for us in terms of space exploration? Oh, I'm sorry, was there a question?
Yeah, I just had a question really quick. So you were talking earlier a little bit about bacteria being in space. I was wondering if you heard about any other kind of microorganisms, specifically viruses.
Sorry, specifically which?
Specifically viruses.
Oh, I don't remember what the latest findings on viruses, though. I'm almost certain that they did experiments on them. I just don't know off the top of my head what. Yeah, okay, here's the record button.
Dang it. Sorry, I gotta hit the button. There we go. Okay. Here for the second half.
Okay, righty. Okay. Before I got cut off, I'm sorry. Was there another question?
Yeah, I was just asking about like viruses specifically in space, just because I've heard there was a professor at the University of Cincinnati that was studying viruses, and he decided that he could get in work with NASA because if you're sending humans into space, you're going to send herpes into space. And I just wasn't sure if you'd heard anything about that.
No, but I'm sure they've done experiments in the International Space Station on it. Yeah. But I just don't know off the top of my head what they found out. But yeah, different organisms react differently in space. I know plants react a certain way. Lower or simpler life forms apparently love outer space for whatever reason. Now, more complex multicellular things. Well, I thought plants actually did okay, but people, primates, not so great. So, okay. Okay. So what does the future have in store in terms of space? Cheaper launches, which is actually great for everyone. There's actually like over a dozen outfits out there. It's in fact more, roughly around 15 in the U.S. alone, of companies that are trying to get spaceships and satellites up there. I mean, the most famous one is SpaceX, run by Elon. But besides them, we've got Spin Launch, which is actually using this giant catapult to send things out in outer space. So what they do is they'll spin an object really fast in that disc-shaped thing, and then it would let go just in time for it to reach that chimney part, and send it off into Earth orbit. They'll spin something up to above the speed of sound. They'll do that by taking the air out of that spin chamber, and just spinning the heck out of it. So that's one. Um, and then we have a whole. Sorry.
So it's like a catapult. So it's like a catapult.
Yep, exactly like a catapult, a high-tech catapult. Yeah.
I think you just like that.
Yeah, but eh, anyway, I couldn't quite make up that part, but yeah, it'll be interesting to see. So this is, they were able to successfully launch a small payload. So now their next step is to like scale this thing up and start working with bigger payloads. I mean, the thing though is most, I mean, a small commercial satellite is about 2,000 pounds. That's even without the internal fuel. So I'm kind of thinking, okay, you're spinning that sucker up to like say Mach 2, and you have an accident in that disk part. There's enough kinetic energy in there to make a really fairly large crater, depending on where it goes. Now, the other interesting thing that about this thing is if you look on the list here, except for Northrop Grumman, most of the rest of these guys are private corporations, which is kind of nice. So a lot more of a private, albeit very rich citizens are actually getting into it. So which is good for the space industry and space exploration in general. Okay, so what else does the future have in mind in it for us? So we've been making good progress on things like ion thrusters. So the nice thing about that is, so the way it works is instead of a chemical reaction forcing out a jet of gas, we're actually creating an electric field and then kind of like just putting in a small stream of gas and having the electric field kind of accelerate it, causing creating an opposite impulse back to the spaceship. The good thing about that is the electric field. I mean, we get the energy from the sun, so so part of the energy is almost free. So these are a heck of a lot more efficient than chemical rockets, which will allow us to go further or have things up there a lot longer. When a spacecraft dies, it's normally not because anything has gone bad with the electronics or something has happened to it. It's usually because they've run out of fuel. CubeSats. When we launch a spaceship, normally there's also enough space within that rocket for other smaller objects, and that's where CubeSats come in. So somebody had a bright idea. Okay, they'll go out to universities and ask them, hey, do you have any kind of like science experiment you'd like to do? We'll stick it on what they call a CubeSat, which is a small satellite about the size of some of them are the size of a Rubik's Cube. The other ones are the size of a lunch pail. And they'll send those, they'll stuff those things in the unused volume of a launch vehicle. So they'll get their very inexpensive way to send experiments up there, and we get some science data out of it. Not the big experiments, but some science data. So that's a good thing. Solar sails, solar wind does exert a small amount of push, but if we're going to try to get to someplace like Mars, which is quite a bit of a distance away, again, fuel is like gold, and any way that you can create movement without having to rely on chemical fuel is a plus. Quantum communication is one of the things that are developing now. Unfortunately, Russia and China is ahead of us. They're able to send a signal from a satellite onto a neighboring country. We're still a little bit behind them, but the good thing about this thing is there may come a time where it will be impossible to hack or intercept the signal in between two entities are trying to communicate. So once this is up and running, the only place where you'll be able to hack anyone would be at the endpoints. So very exciting development, especially in the realm of banking. So transactions are a heck of a lot more secure. Civilian surveillance satellites. This has been going on for years now. So people like Ernst & Young or some of those auditors are using SpySats, civilian SpySats, to validate the accounting numbers that are being given. one of the ways, an example of the ways they're doing this thing is they would actually photograph like say a company is saying that they're producing so many widgets per year. They would actually go ahead and look at that factory and see how many cars are parked around that area. If there's not a lot of cars, then they'll say, oh, okay, there's probably not a lot of activity there, so they might be fudging their numbers a little bit. So again, more of measuring something by measuring their proxy. Space tourism. So we're just on the cusp of commercializing space. The Russians have beat us to it just because they're more amenable to like payouts. So we've already had a couple of folks over on that side. I think the last time somebody went up to the International Space Station on a ride with the Russians, the gentleman paid about $2 million to get on this launch vehicle. But over time, hopefully they'll start putting up dedicated habitat, so we don't have to bother the legitimate scientists trying to get work done up there. Other things are autonomous spacecrafts. One of the things that really makes space travel difficult is that when things go wrong, they really go wrong, and we lose track of the spacecraft. But we're really making a lot of strides in artificial intelligence and autonomy. So let me just share this thing. So this is one of the launch vehicles from SpaceX. It's coming in and it's landing on this barge. So the ship is landing by itself. It's not controlled by anyone. The barge itself is also autonomous. There's nobody on board that thing. So this barge kind of like, chugged along and met the launch vehicle where it's going to land, and the launch vehicle itself managed to make a end-over-end landing on it. I mean, it's a good thing they used AI to do it, because humans probably don't have the dexterity to pull that off. So that's another exciting piece of development, and it's something that us aerospace geeks kind of like get excited about. Okay, sorry. Yeah, there's a question.
Yeah, I don't know if you're gonna know the answer to this. So when that rocket lands on that barge like that,
Huh?
how stable is it once it lands?
So it's very stable, because the way they designed that rocket, it's kind of bottom heavy. So even though it's kind of tall, at the upper section, after the second stage is gone, it's kind of light on top, kind of heavier on the bottom. So it's a little bit steady. And then they sized those feet, the feet that deployed out, they kind of sized it so that it gives it a little bit of stability. So I don't know how to quantify the stability, but they're able to not have it tip over, even though the sea was rocking a little bit. So obviously, if the weather was a little bit worse than what you've seen over there, then they won't be able to pull it off. But it's stable enough on just to land on a normal ocean boat.
Thank you.
Are they landing, I don't know, 80%, 90% successfully?
Well, they haven't. I haven't seen any numbers. So normally the space travel is in and of itself is kind of dangerous, and the way that's quantified is some of the satellites that we launch, we have to insure them. Because something goes wrong, somebody needs to pay for the replacement, and the premium for insuring a spacecraft is about 1/5 the cost of the whole spacecraft plus the launch vehicle. That's how risky it is, because they're expecting 1 out of every 6 launches to fail. So that's why the premium is 1/5. That's how insurance. I'm sorry. Is that right? Yeah, they're expecting 1 out of every 6 to fail, so the premium is 1/5. So that's how the insurance companies make their money. So now, what's Elon Musk's track record? I haven't seen any numbers, so I don't know.
Oh, somebody does.
Oh,
Yeah.
somebody.
Yeah,
Somebody does.
Launches of our
Yeah. Anyone else?
Any other questions?
Huh?
Okay. No? Are you all done?
Yeah, that was it. I just wanted to give a brief primer on satellites and what it's all about. And again, I didn't know what you guys wanted to know, so I'm just here to answer questions. And hopefully, the presentation kind of spark some questions. Sorry.
Can we say hi to Sarah?
Oh, sorry, Sarah's hiding somewhere.
Ah, nuts. All right. Well, anything else? Anything?
I do have a question.
Oh, okay. Yep. Question.
So since we're getting into the privatization of space, with
Uh-huh.
there need to be like specific orbits and such, are there any like governmental or like even UN like requirements for like private citizens with their space travel, or like even like Elon Musk? Like, are there like, I should have to be like a lot of like red tape hoops to go through to actually send a Tesla into space.
Uh, you'll be amazed. Because okay, I, I guess a story would be better to illustrate this point. Once upon a time, there's some rich guy that lives in Palo Alto. This is around the area of Stanford where I live, and normally that's where all the rich people go. People with more money than they know what to do with. So one day, this guy decides, okay, he's going to have a Scud missile, a ballistic missile imported in. So he comes into the customs, and so the custom agent is looking at it and going, I know this is illegal. And the guy goes, show me where it says so. But the point is, right now, the laws governing space are still in its infancy. So, right now, the efforts by all of these private citizens to do stuff out there are kind of like beyond the reach of the government right now. They're kind of ahead of them. So when Elon Musk sent his Tesla out there, nobody could tell him that he can't do it. So
So I have a question about, if a student is interested in doing this kind of work, how do they get started? Do they take an aeronautical engineering degree? What do they do?
Oh, it depends on their field of expertise. You could literally be in any field, and there would be a place for you in the space industry. My field is in mechanical, so I dealt a lot with the rockets, but obviously there's a lot of biology or life sciences majors that have a hand in the experiments that they're running in the space station. Obviously, for the next phase of space explorations, if we send humans out there, then medical degrees would be extremely useful. If we send AI or robotics out there, then computer majors and software engineers would be needed. So there's, I mean, I can't even. It's hard for me to think of a major where someone would be at a disadvantage, except maybe I mean, I don't even want to say liberal arts, because as we start thinking about the laws and promulgating regulations and whatnot, we'll need humanities and uh, 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 social sciences folks to kind of think about those kind of things on how we're going to conduct ourselves once we're out there. So sorry, I can't think of a field that's not needed in space. So if anyone, so if you know someone that's interested, just tell them follow their passion, and there'll be a place for them in outer space.
So, okay, so then how do they find a job or find an ad, right? So there are 10 companies, there are 1,000 companies, there's a website with all the jobs needed by space people. How do you find it? How do you find a job?
Well, thankfully, because of the proliferation of all these civilian companies getting into space, it's as easy as going to LinkedIn. But over and above that, there are companies they'll make it easier for you to get to that spot. Like for example, if someone applies to Tesla, that's under the umbrella of Elon Musk, who's developing all these cool things that will go into space. So working for Tesla will give you a leg up. Working for Google, they're developing a lot of the technologies that we're going to bring up there. That's another one. So a lot of these big companies that has a subsidiary or has their toes in the space industry would be a good place to start. Plus, it'll give that person a little bit of security for where, okay, if it turns out that the space industry isn't what they want, then there's other places within the same company they could go to. So yeah, LinkedIn or one of these big companies.
Thank you.
No
Anybody
problem.
else? Here we go.
Yeah. So
I've read, and I've also talked to someone about, like, the International Space Station, they said it's in continuous free fall.
Yep.
I can't reconcile that in my mind, because continuous free fall to me would be like falling straight down to Earth versus in an orbit. Like a circular path, so how is that continuous free fall?
Well, I guess it's a little bit more of a nomenclature thing. They're technically falling, but they're going fast enough where they actually miss the planet.
Yeah, I don't get that.
Okay, so when a falling body, so if you have zero velocity and you fall, you're going to hit the ground because you're falling straight down. If you have some amount of forward velocity and you're in free fall, you'll hit the ground, but a little bit further away. And now imagine you're going at a speed where by the time you hit the ground, the Earth has moved already.
So what's giving it its velocity?
Oh, when we put things into outer space, we would impart in it some certain amount of velocity. So the rocket would boost it to a specific speed for the orbit that they need to be in. Once they get to that speed, there's not a lot of things up there that will cause it to slow down because there's not a lot of there might be a molecule here or there of air, but not much. So it'll pretty much, there's nothing that will slow it down. So yeah, so it'll just be on this it's continuously falling down, but it keeps missing the Earth. So by the time it hits the ground is no longer there. That's why some people call it free fall. But for me, as a mechanical engineer, I find that thinking kind of like a little bit problematic. So I kind of think of things on orbit as a balancing act between the centripetal force and the speed of the object. Sort of like when you're twirling something on a string. So the string is holding it, but its velocity will keep the string tight. So it's that balancing. It's that balance. I'm like you. To me, having something in free fall is counterintuitive. So I kind of, for me, the way I think of orbits as it's just the perfect balance of the of an object's speed versus the effect of gravity on it.
Okay. All right.
Because for me, I'm like you. For me, when I think of fall, I'm thinking, oh yeah, sooner or later you're going to hit the ground. So that's why I mean, conceptually, I know how that term came about, but to me, I find that term kind of clumsy also.
So if its velocity was too slow, it would hit the ground, and if it was too fast, it would just rocket off into outer space?
It'll break orbit, correct, for a specific altitude.
Okay. All right, yeah, that makes more sense. Thank you.
Okay. Anyone else?
So at the
Alrighty.
beginning,
Wait, one more.
oh, sorry.
Okay.
At the beginning of the presentation, you said your satellite was the size of a semi truck.
Yep.
What was the total capacity of the launch rocket?
The launch rocket, the Russian one, I think had a capacity of like 6,000 kilos.
So how many semi trucks would that be?
The 3, maybe 4. So yeah, so the limiting factor is the amount of volume. So obviously it'd be tough to squeeze a semi truck in there, but the mass of 3 semi truck without the trailer. So probably the mass of 3 semi trucks are what the Russian Proton launch vehicle could send into Earth orbit.
Okay.
Now the impressive thing is back in the good old days of when we during the space race, the old Saturn launch vehicles I think had 3 or 4 times that capacity. It's just a ginormous amount. I mean, they can put a house in orbit if they wanted to, but we no longer have the capability to build those old rockets. So props to those old engineers. I mean, they're really hardcore.
Did you design a satellite for Australia?
Yeah, it was called the Optus C1 spacecraft. So the one I designed for Australia, it had a payload for detecting distress signals from in the ocean. It had that. It also did a little bit of radio signals, and I think there was also one other thing that it did. It was the most amount of payload we squeeze in the same bird. It had it also tracked weather from that same satellite.
Do you have the video of that?
Not no, I don't have that handy, unfortunately.
It's okay, I put you on the spot. It's a cool video.
Yeah,
Anybody
so yeah. All right. Thanks a lot, folks. It's been a pleasure. If you think of like if tonight while you're drinking you suddenly come up with a question and go, oh my God, I should have asked this. Send them off to CJ. I'll try to shoot back an answer. But anyway, have a good rest of your night and enjoy your evening, folks.
Thank you so much. All right, thank you.